In this particular example, they're asking us what kind of intermolecular forces act between two hydrogen iodide molecules. So if I'm going to draw those out here, if I'm going to draw their basic Lewis structures, it's just going to be this, and they're going to be my valence electrons there. All right, that's hydrogen iodide, that's its Lewis structure. Very clearly polar, right? There's a bond moment this way, creating that dipole moment. Very, very clearly a polar molecule. Okay, I have two of these because they say intermolecular forces between two hydrogen iodide molecules. So I'll have another polar hydrogen iodide molecule, and I want to know what intermolecular forces act between these. Now, these intermolecular forces that we are discussing, these four listed here, are attractive forces. So we're talking about forces that attract these two hydrogen iodide molecules together and hold them together to some degree. Could be very strongly or fairly weakly. So there's one intermolecular force that we know is always at play between atoms, ions, and molecules. That is dispersion forces. So dispersion is our automatic answer for all of these problems. It's always going to at least be dispersion forces because there's going to be some type of basic attractive force between all atoms, ions, and molecules. Okay? Let me explain why that is. Let's say, for example, I have a container full of nitrogen gas, molecular nitrogen. Okay, nitrogen is diatomic, so it exists as two nitrogen atoms bonded together. So I have a whole bunch of these N2 molecules in this tank. Well, what's the Lewis structure of that going to look like? I should have 14 valence electrons, 2, 4, 6, 8, 10, 12, 14. There we go. Now the question is, how do I explain what I see when I take this tank of nitrogen gas and cool it down? So if I cool it down, what does it become? Liquid nitrogen. Have you ever heard of liquid nitrogen before? Yeah, it's very cold nitrogen gas. It becomes liquid nitrogen. So that's this, but in the liquid phase. Well, if it's going to become a liquid, what does that mean? If it's a liquid, that means that a whole bunch of these N2 molecules are attracted to each other, right? What do we know about liquids? The atoms and molecules in liquid state, are they really spaced out or are they really close together? They're really close together, interacting with each other, touching. So what force could be holding these together? Because this is nonpolar, so it can't be dipole forces, right? It's nonpolar, symmetrical. It also cannot be ion dipole because neither is an ion. It can't be hydrogen bonding because hydrogen isn't even present. It has to be dispersion forces. Dispersion forces explains it. Even though London dispersion forces are fairly weak, they are strong enough so that if enough energy is taken out of this system, if enough energy or heat is lost and taken out of this system, if I cool it down enough, it slows these molecules down enough that the dispersion forces between them would be strong enough to keep them fairly close and attracted to each other. So just a sidetrack to explain why that is, how dispersion forces alone can explain some of the things that we see between atoms or even on nonpolar molecules. So again, we've got these two polar molecules here. Dispersion forces are at play like they are between all atoms, ions, and molecules. Is this an ion? No, it's not an ion, so we cannot have ion dipole forces. is this hydrogen bonded to either a fluorine, oxygen, or nitrogen atom? No, that's either. So we also cannot have hydrogen bonding. But this is a polar molecule, and I've got many of these, so they're all polar. So because it's polar, not only do I have dispersion forces at play, I also have dipole interactions as well. So I'll just write dipole here. And there's my answer. So how do the dipole forces hold these two molecules in some type of attraction? Well, because this is polar, that means that the electron density is not equal, is not symmetrical, right? The electrons are pulled more in this direction. So that means that this is the negatively charged region of this molecule. This is the positively charged region. Negatively charged region, positively charged region. So that means that this negatively charged region of this hydrogen iodide molecule can form an attraction, electrostatic attraction, or has an electrostatic attraction to positively charged regions of other hydrogen iodide molecules. And so I've got this electrostatic attraction between these two regions here, and there will be a little bit of holding there, okay, because of the difference in charges caused by the dipole or polarity.